Good morning. So today we will talk about the hardest logic puzzle ever, and then after that we will go back into the regular lecture notes. We will start in around 5 minutes. Thanks all for coming. Yeah, good morning all. Thanks for coming. So we will be starting in around 2 minutes. Okay, so let's start. Okay, so first of all, we will talk about this very exciting problem. I will not talk about the solution today. So for solution details, then you can check the OCW recording. But here, what I want is to introduce the problem and give you some key ideas so that if you uh, uh, haven't watched the OCW recording, you may start thinking about and solving the problem yourself first. Okay. Okay, so what is this puzzle about? So there are altogether 3 gods. Okay, so one of the god is an honest one who always tells the truth. Okay, and then the other one is a dishonest god who always lies. And finally, there is a third one, and then we call this god a random god. So this random god will arbitrarily answers you something that is true or something that is false. So it is like this god is not going to listen to you anyway. And then whenever you ask the god a question, he just randomly pick an answer, either true or false, or either yes or no. Okay. So here there are 3 gods here. So let's say this one is Athena, and let's say this one is Poseidon, and then let's say this one is Apollo. Okay. And we don't know who is who. Okay, so at this point, you don't know. Okay, maybe this is honest, but maybe also this is honest. But at least what we know is that exactly one of them is honest, one of them is dishonest, and one of them is random. And then the task of this puzzle is we want to ask the God questions so that we can find out who is who. And then each question that we ask is going to address to one of the God. So we may be asking this God a question, and then we may be asking this God another question, and then maybe we are asking this God a third one. Is that okay? So we can ask the God question by question, but each time we ask one God, and the God that you asked will answer your question. Okay. Now the problem here is that altogether there are 3 gods, and then we are only provided with 3 questions. So you can ask altogether 3 questions. And then there is another problem. Because they are God, we don't speak the same language as these gods. So in that sense, they understand what we are asking, but we may not understand what they are answering. So luckily, we still have some idea what the answer could be. So in God's language, they will answer in da or ja for yes or no, but then we don't know which one is yes, which one is no. Maybe da is yes, maybe ja is yes, we don't know. The only thing that we know is we know one of them is yes, and the other one is no. So what can we do? We can ask them questions expecting the answer to be either yes or no, so that they will be answering in da or ja. Okay, now this problem is very, very hard. It is because there are only a limited number of questions. And then we also have no idea what this da and ja means. Okay. And then there is also a problem because there is a God which is random. So for instance, we may be asking a God something like 1 plus 1 is equal to 2, but then we don't know which God we are asking. Maybe we're asking an honest God. So he or she will answer one of the answer, da or ja, according to the type. But on the other hand, it could be a random God. Random God behaves randomly. So he just listens to a question and then gives a random answer, da or ja. Okay, that's it. So this is this is the most challenging part of this puzzle. Okay, so I'll give you some key idea so that it may help you to solve this puzzle by yourself. So the first key idea is we want to manipulate a non-random person. What does that mean? Okay, so there is a famous puzzle called Heaven and Hell puzzle. So in this puzzle, we have a person, and then this person is known to be either honest or dishonest, one of the type. We don't know which type this person is, but then this person could either be an honest type who always answer correctly, or could be a dishonest type who always answer wrongly. Okay, and then our target here is to ask this guy one question so that we know. So we are in a crossroad. So we are at the road at the junction of a crossroad, and then we want to know which side will lead to heaven, which side will lead to hell, and then we can only ask this person a question without knowing exactly whether this guy is honest or dishonest. Just one question, we can find out which side goes to heaven. Okay, now so if you want to challenge yourself of solving this hardest logic puzzle ever, so let's try to solve this first. Okay, so suppose you have a non-random person to begin with, is it possible to make use of this non-random person and help you to answer something that you want to know? Okay, one yes, no question. Now, once this is done, now the second idea here is that we need to handle the confusion from da or ja. So we don't know whether da means yes or ja means yes. So here, this time, suppose that we are given a non-random God. So it could be an honest God or could be a dishonest God. And this time, we are facing the same problem, heaven or hell problem. And then we want to design a question to ask this non-random God such that the answer will help you to decide which way goes to heaven, which way is not. And then what you are expecting is you are expecting the answer either in the form of da or ja, and then you don't know whether this is yes or no. Okay, so in that case, in the end, what you need is you need to know which side goes to heaven, but in the end, you do not need to know, and there is actually no way to know whether da means yes or ja means yes, and whether this God is an honest God or a dishonest God. Okay, now if you can solve the first puzzle, heaven and hell puzzle, for non-random person, now try this one. Okay, if you can also solve this, then you are very close to success. So the heaven and hell problem when you are asking a non-random God. Now the third idea that we need here is, so here the first two parts actually tell us that if we are dealing with non-random person or non-random God, it is rather easy. We can extract information from this non-random thing, okay? So the third key idea here is that we have three gods to begin with. So we want to somehow find a way to identify a non-random God. We don't care. We don't care whether this God is honest or dishonest. Just any non-random God will be something good for us. And then to solve this, okay, in the lecture we have a two kings and one jack problem. So in this problem, so let me describe the problem briefly here so that you have an idea of what it is. So there are altogether three cards. Two of them are kings and one of them is a jack. So all the cards are face off so that you don't know which one is which. And then you have a friend to play this game with you. Your friend will pick up one of the card. Okay, so your friend selects one of the card. And then he looks into the card and see what it is. Now, if he sees the king, so if he selects a king, then your friend is going to speak honestly for the next thing that you ask him. On the other hand, if your friend picks a jack, then your friend acts as a random person, so he can speak truth or he can tell lies for the next question that you ask him. Okay, so after your friend selects the card, then it will determine his type. And then after that, your task is you ask your friend a question and find out. You can ask your friend a question and find out a card that contains the king. So altogether, there are two kings and one jack, okay? And then your friend selects one of them. So altogether, there are still three cards, right? And then you want to ask your friend one question only, and then you need to decide one of the card which is always a king. Okay, so you need to do so. Okay, so because your friend could be a random person, then whether his answer is yes or no could be meaningless to you. So you need to find a way to solve this. If you can do so, then we have the three key ideas together. Then actually the key idea number 2 and number 3 here are the most important one. One is like a warm-up. If you know one, then you can have 2. Okay, now 2 and 3 combined will give us the full strategy here. So this is the strategy. We are going to ask 3 questions. So the first question is, we want to identify a non-random God. And then let's say this God is G. Once we have a non-random God, we can make use of this God. We can manipulate G, ask G a question, although he is answering or she is answering in Da or Ja. But then by number 2 key idea, you can find out, you can extract information from G so that you can You can find out whether G is an honest God or a dishonest God. Once you have done with the second question, then you can ask the same God, this G again, to find out the type of another God. After 3 questions, you will know the type of 2 of the gods. So that means that the type of the third one can be determined as well. So this is one way of solving the hardest logic puzzle ever. So try. Yeah, this is fun. Okay. So if you have any questions for this one, yeah, you can send me questions, and then yeah, I will make it either answer you directly or we can put it into the next tutorial to talk about this. Okay, so this is part 1. Okay. Now let's get back to the lecture. So okay, so this week, yeah, we don't cover a lot of things here. Okay, so let's see. Okay. But we are starting a new topic called predicate calculus. So this is like, so we are starting with logic proposition before, and now we are going one level up to design something that can express more complicated idea in logic. Okay. So in this set of lecture notes, we will talk about what is meant by predicate, what is quantifier. So these are the topics for today. And then for the next week, so we will talk about the binding applications, and then again we have logical equivalences for these new types of logical proposition. Okay. So what is predicate? So predicates are, okay, so let's see. Okay, so in a lot of math arguments, we will see sentences containing variables. So for instance, we can see something like x is greater than 0. So x is a certain variable. We don't know what its value is, but x is a certain variable, and then we want to say that, oh, x is greater than 0. It could be true, it could be false. When the value of x is fixed, then we know that whether this is true or false. Okay. Or we can have something like x is equal to y plus 3. So we have x here and y here, they are variables. And then we have computer x is functioning properly. So this part is the variable that we have. And then the variable that we talk in the sentence here, they are the subject or the subjects here. So we have 2 subjects here. They're the subject of the sentence. And the remaining part of the sentence that tell us the property of the variables or the relationship of the variables is called the predicate of the sentence. Is that okay? So for instance, let's say x greater than 0. So we have the sentence here. X part is the subject, and the remaining part greater than 0 is the predicate. Or for another one, let's say this one, x and y, they are both subjects, and the remaining part like equal and then plus 3, the remaining part that relates the property of x and y, then these are the predicates of the sentence. Okay. Now, one thing that we know here is that when the value of the variable is known, is assigned. So as in this example, so let's say when the value of x is known, then this sentence is not just a normal sentence, it becomes a proposition. And then we can talk about its truth value. So for instance, when x is fixed to be 1, then this becomes the proposition 1 greater than 0, and it will be true. When the value of x is set to be -7, then this becomes the proposition -7 is greater than 0, and the truth value will be false. Okay, so depending on the value of x, the truth value could be true or the truth value could be false. So we can talk about this like this is a function of x. Yeah, right? So by plugging in different values for x, we have different results. So we can represent this as a function. So for instance, something like p of x, we use p to represent just any variable. We can give it a name, right? So here we can use p of x to denote the whole proposition function here. So this is called a propositional function because by fixing the value of x, every time we will get a proposition. So this is a function that generates propositions for different values of x. Is that okay? So for instance, Yeah, so we have done this example, a similar example before. So Px this time denotes the whole sentence x is greater than 0. And after that, we can talk about what is P0. So P0 stands for, we plug x to be 0 here. So P0 is the sentence 0 greater than 0. So P0 has the value false. And P1, it has the value true. Okay? And similarly, for this sentence, we have two subjects, x and y. So we can use a propositional function with two variables inside. So let's call it q of x and y, okay, to represent this sentence. And once the value of x and y are both known, then we know the truth value. So for instance, q12 will represent 1 is equal to 2 plus 3, this sentence, and then this is false. And q30 represents 3 is equal to 0 plus 3, so it is a true sentence, a true proposition. Okay? Okay, now the next part is about something called quantifiers. So here in English, we have words like all, some, many, none, few, something like this, to express some property about whether the predicate is true over a range of subjects. So for instance, we may say, oh, all of us are happy. Okay, so in order to say something like this, so we are actually checking whether for every one of us, are we happy? So if we are happy, if I'm happy, you are happy, he is happy, she's happy, and so on and so forth. If all of us is happy, then we get one thing. This is going to be true. Okay, but on the other hand, if some of us, if one of us is not happy, then in that case, this will be false. So in that sense, in English sentence, we are actually using some common words like all, some, many to express the property of, let's say here, we say a person is happy. This property over a range of subjects. Over a range of subjects, like the example here, we are talking about over all the people in this class. Is that okay? Now, these words, all, some, many, they are all called quantifiers. And then in math, then we also want to borrow this idea. And then we have two important quantifiers that are very commonly used. So the first one is called universal quantifier, and then the next one is called existential quantifier. So we will talk about this now. So universal quantifier, universe means that this is the big universe. So we consider all the things here. So universal quantifier is something like we say something is true, that we want to declare that the property is true for all. So for all the possible values of a variable that we can take, for all the situations that we can imagine. And then, so here, so let's see an example first. So here we have z times z plus 1 times z plus 2 is divisible by 6 for all z. Okay, so we want to mention that for any z that we imagine, then this is going to be true. So we want to have this for all. This is a quantifier. But then when we talk about this z, we also want to specify what are the values of z that we are going to focus on. So here, in this particular example, we look at only integers. Okay, so we consider only integers. So the z here must be an integer to begin with. So we don't care about whether z is a real number or a complex number or whatever. So we look at integers. So this part that specifies what kind of values that we should look at is called the domain of the value that we are looking at. So the domain here is the integer domain. So the domain here is all integers. So as another example, so this is another mathematical statement. So we say q squared is rational. So rational means that it can be expressed as a ratio of two integers. So q squared is rational for all rational number q. So here, again, we see the sentence or the quantifier for all here. We want to mention that for any rational number q that you can imagine, the value of q squared is also a rational number. So, okay. The third one, so altogether, this one becomes, this whole thing, it becomes a proposition although originally q squared is rational, is a propositional function because the value of q is not fixed. We don't know. But here, with the quantifier that specifies what we are looking at, then this becomes a proposition. It is because this corresponds to the proposition of we look at whether the first q that we choose, q squared, is rational or not, and then whether the second q that we can imagine, whether q squared is rational or not, and so on and so forth. If all of them are true, then the whole thing is true. So it is now specified because we know what kind of q that we are looking at. So the third example is RQ is greater than 0. So this time, again, we see for all positive real number R. Okay. Now notice that it is very important to specify the domain. Yeah. Otherwise, we can have problems. Yeah. Let's see. We have so we will talk about the problems later. Yeah. And then you can try to prove every one of them they are true here. Actually, these are examples, and then they are representing true propositions. Yeah, you can try to prove them. But here it's not necessary to prove them now. Okay, yeah, because we are not talking about how to prove things, but at least we can understand that each of them is a common mathematical arguments we will meet daily, and then each of them make use of the universal quantifier with domain. Okay, that's it. Okay, so here this describes the definition of a universal quantifier and the shorthand notation. Okay, so suppose that we have a propositional function p of x, and then the universal quantification for p of x means px is true, okay, for all values of x in the domain that we imagine. Yeah. So this becomes, so originally px is a propositional function, but the whole sentence now here, because we have now quantified, we are looking at all the x together and then consider them all together at the same time. So this becomes a proposition. Okay. And for shorthand notation, so here it says that for all value of x, we use this notation. This is an upside down a for all x p of x. Okay. Now this is for all because all is like a. Okay, so we use an upside down a to represent the value. So the to represent this keyword for all. Okay, it reads as for all x px. Okay. So this becomes a proposition, and it will be true if it is really true. For every value of x that we can imagine, p of x is always true. Okay, but on the other hand, this whole thing will become false if we can find some x such that p of x is false. Now, if this is the case, if for all x px is false, and then we can find some x that makes the proposition false, then we call this a counter example. Okay, so this example is going to counter your claim that this thing is correct. So this thing is going to be wrong. I give you an example. So this is a counter example. Okay, so in some sense, okay, for all x px, you can imagine that this looks like something like this. Suppose that you can have x1, x2 up to xk that you can pick in the domain. Then for all x px, then it is the same as saying p of x1 and p of x2 and p of xk up to p of xk. Yeah, you can see that whenever all of them are true, then it is true. But if one of them is false, or if at least one of them is false, then it will become false. Okay. So let's see. Okay. So let's see this example. So what is the true value of for all x is less than or equal to 10 when the domain consists of all the positive integers not exceeding 3. So here, we look at all the x that we can imagine, but the domain here is about all positive integers not exceeding 3. So it talks about x could be 1, x could be 2, x could be 3, right? So to determine whether this is true or false, it is the same as we let x less than or equal to 10 to be p of x. So we ask whether p1 is true, whether p2 is true, whether p3 is true. If they are all true, then it is true. So in this case, it is true. Okay. Okay, and then the next example will let us see that the domain has to be specified clearly, because otherwise we could have different interpretation of the sentence. So this time the propositional function is x squared is greater than or equal to x, and then we want to ask whether this is true. For all x that we imagine, x squared will be greater than or equal to x. Okay, now the first part says, suppose that x that we are choosing comes from all possible real numbers. So we consider all real numbers. Is it true that for any real number, for all the real numbers that we can select, x squared will be greater than or equal to x? Now a quick checking tells us that it is not true. Suppose that we set x to be 0.5. So 0.5 is a real number, right? The square of 0.5 will be smaller than 0.5 because you are taking half of half, so it is smaller. So in this case, 0.5, if we plug x to be 0.5, it will make x squared greater than or equal to x false. So in this case, 0.5, the value of 0.5 for x is a counterexample for this sentence to be correct. But on the other hand, if we focus on the domain that consists of all the integers only, we ignore the non-integral real numbers, then suddenly this will become true. It is because, okay, so this is the proof. Okay, for the second part, it is true. It is because we can see that using our algebra, x squared greater than or equal to x happens if and only if x times x minus 1 is greater than or equal to 0. And then this happens if and only if x is smaller than or equal to 0 or x is greater than or equal to 1. Now, these are all equivalent statements. Now, when x is an integer, it must either be less than or equal to 0 or greater than or equal to 1. There is no way to find an integer that is not falling into this range. So if there is an integer not falling into this range, the value of this integer must be strictly between 0 and 1, and it is not possible. So in that sense, it is impossible to find an integer that gives us a counterexample here. So that's why this is going to be true. Okay, so this is the true thing. Okay. Now, so this is about universal quantifier. So we talk about the next part. So this is another type of quantifier. We call it existential quantifier. So existential quantifier says, okay, a certain statement is true for some value. We don't need every value, but we need to find at least one value that we fix for a variable. It will make the whole statement true. Okay, then in that case, we call this existential quantifier. So for instance, let's say this example. So we have 2 to the power 2 to the power z plus 1 is a prime for some non-negative integer z. Okay, so as long as we can find some non-negative integer z that makes this to be true, then the whole thing is true. Otherwise, this thing will be false. Okay, now interestingly, yeah, this sentence is true. Yeah, it is because, so we can find, for instance, let us say we set z to be equal to 1. Okay, 2 to the power 2 to the power 1 is equal to 2 to the power 2. Okay, so this part is 4 when z is equal to 1. 4 plus 1 is a prime number. Yeah, so in this case, we don't need every value of z to be correct. At least when we find some value of z to be correct, then it is true. So in this case, it is true. Now again, like the universal quantifier, we need to be careful about the domain. Okay, so here the domain here is we can pick all integers that we want. Now the next one is r to the power s is rational for some irrational numbers r and s. Okay, so here this time we consider r and s are both irrational numbers, and then we want to ask, is it true that we can select some particular r and some particular s, they are both irrational, such that r to the power s is rational? Okay, so again, this is a mathematical statement, and then this time we are using existential quantifier. So later when we are talking about proofs, okay, yeah, we will show that this is actually true. So we can really find some irrational numbers R and S such that R to the power S becomes rational. Okay. Okay, now the shorthand notation. Okay. So suppose that we have a propositional function Px, and then we can talk about the making it into a proposition using the existential quantifier. So this time the proposition will become of this form: P of x is true for some value of x in the domain. Okay, so this is the proposition here. And then the shorthand notation here is that we have this notation. This is actually the E, the capital letter E, flipped left, right. So this is the mirror image of the capital letter E. So we have it reads as there exists x, P of x. Yeah, why we choose x? Why we choose E? Because E is the beginning letter of exist. Okay, so like previously, we choose A because A is the beginning letter of all. Okay, so this is exist. Okay, so Px is a propositional function, but then there exists x, Px will become a proposition. And this one is true whenever we find some x that makes it true. So if you can find an example, this time a positive example that shows that it is true. But on the other hand, if we cannot find any example that makes P of x true, then in this case, the whole proposition is false. So here, the proposition is false if and only if P of x is false for all values of x. Okay? So this time, if we interpret this using, so suppose that this time, let's focus on a limited domain. Let's say the value of x can be chosen as x1, x2 up to xk. So these are the possible values that we can pick as x. Then the value of there exists x px will be the same as px1 or px2 or px3 up to pxk. Yeah, because if any one of them is true, then it is true. But if all of them are false, then they are false. So the whole thing will be false. Okay. So for instance, how about this one? So what is the true value for there exists x when x is, so the proposition function is x is less than or equal to 0 when the domain consists of all positive integers not exceeding 3. So here we look at all positive integers not exceeding 3, so there are only 3 choices. Either x is 1 or 2 or 3. So here we are asking what is P1 or P2 or P3. Now P1 is false, P2 is false, P3 is false. So the whole thing, there exists x, x is less than or equal to 0 is false. Now similarly, we have another example that emphasizes the importance of the domain. Okay, so let's look at this sentence. There exists z such that z square is greater than or equal to 10. Now, if we consider only integers, positive integers not exceeding 3, then 1 square, 2 square, and 3 square, they are all not greater than or equal to 10, so it is going to be false. But on the other hand, but here, let's say this is about all positive integers, so this is tricky, so we just consider 1, 2, 3. But now the second part here is we are talking about all integers not exceeding 3. Now, in this case, we can have a larger group of numbers that we can consider for x. This time we can pick minus 100. Okay, so if we pick z to be minus 100, then the square of that will suddenly become greater than or equal to 10. So in this case, if the domain is like the second case, then the whole proposition will be true. Okay. Okay, there are 2 more slides to go for today. Okay. So here, sometimes it is further shorthand notations. Okay. So sometimes we want to specify a further restriction on the domain that we have. So for instance, suppose that the domain originally will focus on all integers, but then we can write something like this as a shorthand notation. Someone will write something like this. It says that for all x less than 0, x squared greater than 0. So what does that mean? So here, it says that originally we talk about for every x to consider, but we have a new restriction that we want to add on the domain. So instead of just looking at all the possible x in the domain, we focus on those parts such that x itself satisfy this relationship x is less than 0. So we consider all the possible x which is less than 0, and then we want to check whether for these x, whether x squared is greater than 0. Is that okay? So this part, it adds up some further restriction on the domain. And similarly, this part, it says that for all y not equal to 0, and then the propositional function after that. So here we want to restrict the case that we don't talk about y which is 0. We only talk about the case where y is always non-zero. And here the last one, it says that there exists z greater than 0 such that z squared is equal to 10. So this is another proposition. And here the restriction is we have z has to be greater than 0. Okay, now notice that by adding this restriction, it doesn't actually, it is just a shorthand notation. We can always represent a proposition like this. So this is a proposition with quantifier, right? We can always represent a proposition like this by using the natural case. We don't have restriction at all. By translating this into another form that is looking like we just have quantifiers and we just have propositional function. So how can we do? So actually, for all x greater less, so let's see this example. Okay, for all x less than 0, x squared greater than 0 means that we want to consider every x is in the domain with x less than 0, and then we want to claim that x squared is greater than 0. Although we don't know whether this is true or false, but then this is a direct translation of what this says. Okay? And then we can change this one, this shorthand notation, into a proper proposition in this form. So we can just keep the for all x part, and then we can plug in this part. This is the restriction inside the propositional function. Okay. So we make the propositional function a little bit more complicated by putting something like the restriction and then implies the original propositional function. So here we change this one into this one. Now the whole idea here is that this part is like acting like a filter. Okay. So whenever x is less than 0, which means that it is within the restricted domain, we need the next part to be correct. But on the other hand, whenever x is not inside the domain, then we don't care. We don't care. We don't care whether the latter part is true or false because this is outside the domain. And in that sense, we want to make this not affecting the truth value for the whole thing. Now, if you still remember, for all means that it is a bunch of propositions and together. So in that case, whenever x is less than 0, we hope that the case here, the corresponding case here, will be true all the time. So that's why we use a imply here. This is the property of imply. Okay, on the other hand, for there exists, so this is a there exists type here. So there exists a restriction z is greater than 0, z squared is equal to 10. So this is a propositional function. This is the restriction. Now this time we can translate this into this sentence, the regular sentence. So we just keep there exists z, is that okay? And then the restriction part comes into the propositional function. And this time we put it here, z is greater than 0, and then and the corresponding propositional function, original propositional function, z squared is equal to 10. So again here, this part is acting like a filter. Okay. Okay. So what we want here is that we want to make sure that there is always, so in order to make this true, we really want to have some set that is falling inside the domain, and at the same time, it will have the relationship following the propositional function, z squared is equal to 10. But for all the remaining set that is not inside the domain, I don't want it to affect the truth value of this part. Now, if you still remember, so there exists is a bunch of proposition all together. So in that case, whenever z is not within the domain, we hope that the corresponding proposition will have a false value. so that when it is OR with the others, then it is going to be not affecting the others. So making sure that whenever Z is not in the domain, I want to get a false. That's why I have this part here. Z is greater than 0 and something. So whenever Z is not inside the domain, this is false. False and something will be false. Okay. Okay, so this is somehow a little bit complicated, but then this is actually the most complicated part for today. Even more complicated than the hardest logic puzzle ever. But I hope you can clarify this. So once it is done, it is clear, then you will be really, really happy. And then check out the OCW recording for the details. And then again, if you have any questions, please, feel free to ask us. Okay, so that's all for today. Okay, and then so let me quickly check if let me quickly check if there are any questions. Yeah. Okay. I see one question, so let me quickly address the question here. Px, so that for all x, p shouldn't be for or then it means there exists and this one is true. Okay, thank you. Right. For all means every single one is true. Right. Very good. And then okay. Okay, so does quantifier represent symbol or the entire result? Oh, so the quantifier is bound. It is attaching to the variable. Okay, so here, so let's see an example here. Sorry, excuse me. So let's see. Okay, so for instance, we may have a complicated. So this is the next week. So here, let's see. This is a propositional function with two subjects, right? Okay. So in this case, we can have a sentence like this. So this is for all y there exists x plus y is equal to 0. So here, this for all is binding to the variable y only. And then this there exists is binding to the variable x only. So here, the whole sentence is for all the values of y that we can imagine, there will be some x that we can find such that x plus y is equal to 1. Okay, so this is a sentence that reads like this. Okay, so whenever we so this is something like this. So the for all is binding to the variable. The there exists is binding to the variable. Here. Okay, let me see if there is a further question here. Okay, why don't we use for all? Okay. So someone asked, why don't we use just a lot of n? Because here the x here could be something that we cannot list out. Maybe we are considering all the x's in the of all the real numbers. Okay, we want to make it short. And we can never list out all the possible x, right? So there are not just infinite number of them, and then later we will also see that it is not very correct to say that we can list out all the possible real numbers. So just take it. So for all is a concept that we are looking at all the possible cases at the same time. Or for each case it is true, then for all will be true. Okay, so I think that's all for today. Thanks a lot for coming. So we will meet again next week. Okay, and then we will prepare for because we are done with the first set of lectures. So we will be sending out assignment 1 for your reference. So they don't need to be turned in, and then discuss with your friends to work on it. That's it. Thanks. See you.